Hello everyone. This is a supplementary lecture to module 1 where we will discuss some additional arithmetic of floating point numbers. So in floating point numbers we have seen how to represent any decimal number into a floating point number, but we are still curious that how to do multiplication, how to do addition, subtraction in floating point numbers. So in the supplementary lecture we will discuss all these things. Please be clear that this supplementary lecture is an optional lecture. It's not part of our regular syllabus. Whatever we are teaching here, it won't be given in the exams or quizzes, but it is still worthy to go through this lecture once. One, it will clear your curiosity. Second thing, you will get to know at least some aspects that how addition subtraction is done. Sometime it may be useful in future if required. So let us first see how addition or subtraction would be done in a floating point number. It would be done in the similar way, the way we do addition or subtraction in decimal numbers which are represented in scientific notations. So first step we should do, or what we do is, first we align the exponent to the larger exponent. So before even first step, the zeroth step is because our floating point number is represented in a 32-bit compact format where some bit is sign, some bit is mantissa, and some bit is exponent. So first of all we extract all of these bits. We extract sign bit, we extract mantissa bits, and we also extract exponent bit, and the mantissa is also converted into significant. Okay, so after that you see, when we are doing addition, we know that the addition, like whatever is the larger number, we would be adding the smaller number to larger number, so the exponent of the smaller number would be aligned or adjusted to the exponent of the larger number. Okay, so how it is done? It is done by shifting the significant of the smaller number in right direction. In right direction means in right, shifting it right by the difference of two exponents. So after this alignment is done, now we need not to worry about the exponent part. We only need to add the significance. So if we are performing addition and the sign of both these numbers are same, then we have to perform addition. But if the operation is addition but the sign of these two numbers are opposite, let's say one of the number is positive, another number is negative, then we have to perform subtraction. Now again remember that these both of these two numbers are represented in sign magnitude form, or there is only magnitude which is presented, sign is present as a separate bit. So we have to create, if we want to use 2's complement arithmetic, then we have to create 2's complement notion for both of these numbers and then perform these addition and subtraction. Third thing, after doing addition or subtraction, then again we have to normalize. Normalize means we have to represent the number in the normal scientific notation or a standard scientific notation. In standard scientific notation, so there has to be only one non-zero number, that means 1, before decimal point, and after that any number of zeros or ones can be there. So if there is something required to be done for rounding, that would be done in step 4. So in step 3, along with doing normalization, so if there is any other correction required, so for example because in after normalization it may be the case that the number cannot be represented using the range of floating point number represented using that, let's say, single precision format or double precision format. So we also do overflow and underflow check. So if the number is larger than whatever is the limits, then we also give a error and we terminate the process here itself. Or if there is an overflow, then also we give the error and we terminate. But if there is no overflow, there is no underflow, then we go for the fourth step, which is rounding. Rounding means if the number of bits after, let's say, number of bits in the mantissa is more than the number of bits which are there in that format, then we have to round or we have to remove the extra bits. Okay, because after rounding we also sometimes add +1. So because of that rounding, there may be again normalization required. So if the number is not normalized, we go back and go to step number 3 to normalize. So to understand this, let's take one small quick example. So let us say these are the two numbers. I am directly representing in the scientific format. So that means I have already extracted my mantissa bits, exponent bits as well as sign bits. So these two numbers are 1.000. So this is in the format which is like significant is already added. So my step 0 is already done, where I have added significant, I have extracted mantissa exponent, and this exponent also you see is the processed format. So that means let us say it was a single precision number, then 127 is already subtracted from the whatever exponent I get from that 32-bit number. So so this is the scientific notation or the normal notation of these two numbers. Now you see one of the number is 2 to the power minus 1, another number is 2 to the power minus 2, and this number is positive number and this number is a negative number. So if I want to do addition, so effectively I need to subtract, but in the first step I need to align. So in align, which number is the larger number? The larger number is this one, which is 2 to the power minus 1. 2 to the power minus 2 is always lesser than 2 to the power minus 1. So I need to shift by 1 bit. This number I need to shift by 1 bit. So in step 1, I have to make the power of this number as 2 to the power minus 1. So that means I need to multiply. So in a very general case, if the difference of the larger number, the difference of exponent bits of the larger number and the smaller number is n, then I will shift the significant n times or n bits in the right direction. Okay, so the next step is after now both of these two numbers are aligned. So that means exponent of both of these two numbers is 2 to the power minus 1, 2 to the power minus 1. Now I can perform the addition or subtraction. So because this number was minus, this was positive, so the number in step 2 I need to perform this 1.0 minus 0.111. So this arithmetic I need to perform either using 2's complement or using the direct subtraction. So here I am directly writing the results. If we have to perform this using 2's complement, then we have to take 2's complement of these two numbers. So basically we also need to add 3 zeros here, so the decimal point will match, and then we will take 2's complement. But now I am directly writing the result. So here we also know intuitively that 1.0 minus 0.001 will be 0.001. Okay, so in the third step we will check whether it is underflow or overflow. Yes, of course it is not underflow, neither overflow, so we will go ahead and normalize. In normalization, this number need to be converted into a normal or scientific notation, standard scientific notation. So that means this has to be shifted. In this case, this has to be shifted left, and whatever number of bits we are shifting, that we will add here. So because we are shifting it by 3, so we will subtract 3 bits here and it will become 2 to the power minus 4. and then rounding. So because if we are representing this number is a single precision number where number of Mantissa bits are 23, so we need not to do anything for rounding, and this can be written as the result 1.0 into 2 to the power minus 4. Okay, so this is how addition or subtraction need to be done. Now let us see how multiplication need to be done. Multiplication will also do multiplication in a very similar way, the way we do it in our decimal numbers represented in exponent forms. So try to remember how do we do multiplications in a decimal form. So first we will try to multiply, or we will add the exponents, and we will multiply the significants, that is the second part, and a third we will again normalize, and fourth we will round. So the steps are very similar to whatever we did for addition. Okay, and after rounding, again if it is not normalized, then we will go ahead and normalize, and then we will again round, so on and so forth. So until it is normalized. Here one additional step would be that the sign bit would be set after all of these things by seeing if the multiplication of two numbers were two positive numbers were multiplied or two negative numbers were multiplied. Then the sign bit would be sign bit would be 0, that means number would be positive. If one of the number was positive, another number was negative, then the multiplication would result in a negative answer, so sign bit would be 1. So sign bit is treated separately in whole process, otherwise all of these numbers are treated as magnitude. So let us try to understand this with an example. Again I will take the same example. So 1.000 into 2 to the power minus 1 is multiplied with minus 1.110 into 2 to the power minus 2. So first step is we are adding the exponent. Now here I can add the exponent. Minus 1 plus minus 2 is the exponent here, so total exponent is minus 3. Now again remember that in our standard or IEEE 754 single precision or double precision representation, exponent are represented using biased numbers. So if we are using those biased number, we need not to subtract the bias in all the cases. What we can do is we can simply add those two numbers and subtract the bias. So let us say in the bias case, this would have a bias of this would be represented using 126, because bias was 127 minus 1 is 126, and this would have bias of 120, this would have exponent of 125. So we will simply add the two exponents, and then whatever is the result we will subtract bias, that means minus 127, whatever is the result that we can keep as a exponent. So this subtraction of bias need not to be performed when we were doing addition and subtraction, because their exponent was a relative term. Okay, higher is the exponent, that means larger is the number, and when we were doing addition and subtraction, we can simply see the relative difference between two exponents, but here because we need to add two exponents, that is why one bias is subtracted. Then after that, multiplication part. So first we have created the significant 1.000 into 1.110. So then these two would be multiplied. Now I have directly written the multiplication result, but the way this can be multiplied is, so we can remove this decimal point and we can treat both of them as 4-digit number. Okay, so we can treat both of them as 4-digit number and then simply multiply. And after multiplication, the decimal point need to be added after 6 binary digits. So after 6 bits we have added I think, yeah. So this need to be added after 6 bits. I think this 10 is redundant here, but yeah. So this has to be added after 6 bits because of the standard rule of multiplication. Now after this step, then we go for normalization. So because this number was already represented in normalized form, so nothing to be done for normalization. Otherwise, during normalization, sometime we have to shift bits left or right, and there is no overflow or underflow here, so that's why we are not doing anything. But there is a good likelihood that overflow and underflow can occur in multiplication, because multiplication would require this addition of this exponent, and sometimes these exponents jump out of the range, and then these numbers cannot be represented in the multiplication itself, in the range itself. So we have to say that there is overflow and we exit from this step itself. So after doing normalization, then we do rounding. Here rounding also need not to be performed, because the number of significant bits or number of mantissa bits are still less than the mantissa bits which are required or which are possible in single precision numbers. And here the sign is -1, because this number is negative, this number is positive, so we can represent the result. So this is a negative result. Yeah, this is also a small mistake here. So this is how multiplication and addition is done. Now let us see, if rounding need to be performed, then how do we do rounding? So IEEE 754 standard, it defines that there are 4 possibility of rounding. So one rounding is round towards 0. This is also called truncate. So truncate means that whatever number of bits after significant bits are there, we simply drop them. The second is round towards positive infinity. The third is round towards negative infinity, and fourth is round towards nearest even. So in all the rounding cases, we can divide our mantissa or divide our fractional part into 2 parts. One is what is significant or what need to be added in our representation. The rest of the bits could be represented as residue bits. Okay, so residue bits, based on the residue bit, sometime we need to add +1 to the least significant bit, or +1 to the least significant part of this mantissa. Okay, so let's quickly see that in case of we'll see that how and when we add this +1. So we can classify this into if the number is positive or a number is negative. In case of truncation, that means rounding towards 0. So the original number, whatever is the residue bits, because we are rounding towards 0, so the number we are generating after rounding should not be bigger, or should not be like it. So whatever, it can simply be called we want to go towards 0. So that means if the number is positive, then also we leave the residue part. If it is negative, then also we leave the residue part. While in whenever round towards positive infinity, so that is another case. In round towards positive infinity, if the number is positive, then we will increment the significant. So which essentially means that whenever we want to round towards, whenever this mode is there, round towards infinity, that means the number has to be rounded towards infinity. Means if the number is negative, then whatever is the residue part we can leave, because that number would be closer to positive infinity. Okay, but in case of the number is positive, then we'll increment this significant by +1 so that the number is now closer towards infinity. Now the third mode is round towards negative infinity. In this round towards negative infinity, if the number is positive, and then we compare these two things, either the number, if we truncate the residue part, then it is closer to minus infinity. So that means we don't add 1. But if it is a negative number, then we add 1 to the whatever is the residue. If residue is more than 0, then we add +1 to the significant, so that now it is closer to minus infinity. And round to nearest is the most popular one which is being used. So this is a very standard method which we have used in our decimal points also. In decimal point, the way we do is that if the residue is more than 0.5, then we add +1. So how do we know here that a residue is more than 0.5? So that means in my residue bits, in binary, if residue bits first bit is 1, that means first bit is 1 and any other bit other than first bit of residue is 1, that means the number is more than 0.5. So if number is more than 0.5, we will always add 1 to the significant. But what if number is exactly 0.5? Then we will see that if my significant is odd, then I'll add 1, otherwise I won't add. So how to see that if significant is odd or even? Significant means lower MSB bit, so lower significance, least significant bit of my mantissa. If it is 1, then I will add 1, otherwise I will not. So let's try to understand this with an example. So let's say that the result need to be rounded to 2 bits. So let us say these are the input numbers. Now I am marking the residue bits in red. So if it is truncate, then I will always remove the residue bits, will not do any other. So whatever is the number given other than residue bits, that would be given as the answer. In case of positive infinity, now 1.01 and then 0.01 would be added. So that means in the least significant place I will add 1. Because I have added 1, it will become 1.10. And so here, round towards positive infinity, I am not caring what is the size of my residue. Even if residue is very small, then I am adding 1. So it's also very similar to ceiling function of my C. And truncate could also be seen as the floor function of my in C language. Round towards minus infinity. In minus infinity, because we can see from this table, or we can simply see that if I want to round towards minus infinity, because I want this number, the final number, to be closer to minus infinity, so that's why I will leave this residue, I will not do anything. In case of round to nearest, because this residue is lesser than 0.5, so it is discarded, nothing is added to my significant. So in this case, in the negative, this number minus 1.01001, rest of the results are same, but round towards plus infinity, I am not doing anything because the number is negative. But round towards minus infinity, I am adding 0.01, so that the final number is 1.10. Okay, so consider this case 1.01101. So truncate, we are leaving these bits, and round towards infinity, because there is a residue which is more than 0, I am adding 0.01. Round towards minus infinity, because the number is positive, so I am discarding it. In case of round to nearest, the 101 means the MSB of residue is 1, so that means the number is 0.5. And if any other bit in the residue is 1, so that means it is more than 0.5, so I have to add 1, so this should be actually 1.10, so this should be 1.10. Okay, so the last case, if my residue is exactly 0.5, 100, or all the zeros after this one, so residue is exactly 0.5. In truncate, I will simply remove this 0.5. In case of plus infinity, I will add 0.01. In case of minus infinity, I leave it. And in case of nearest even, I will see the last bit of my significant is 1, so that means it was odd, so I will add 0.01 to make it even, so the number would be 1.10. So one thing why we will add this, while we will make this number as even, so there is nothing technical about it, it is more like a historical way of doing things, and that is why we add 0.01. So this is how rounding is done, and rounding would be done because of multiple reasons. So whenever number of significant bits, so for example, whenever we are converting from double precision floating point number to single precision floating point number, we may have to do rounding. As a result of multiplication, sometimes we need to do rounding. So all these roundings are become important, because even these small significant bits are important whenever we are doing multiplication or division. So that's why what mode is there, it is important. The second thing is how to decide this mode. So mostly it is the hardware specific feature. Whenever it is implemented in hardware, we either it is configurable, we need to say that which particular rounding mode is being used. Most in a default or in a typical calculation, round to nearest is the most popular mode which is used in the floating point calculations. So with this I would like to close. Thank you very much.